The major concept this week in class is superposition. And as we looked at the general superposition handout, the way we are going to apply superposition is to solve an actual structure as a summation of a composition of other structures. Now, those structures are going to be related to each other very closely. The actual structure needs to be classified as either determinate or indeterminate. So we begin here with a structure that is determinate. So this simple cantilever has 2 point loads on it. You can solve for anything in that cantilever using statics. We can find external supports. We can find all of the internal forces. And how we would solve this using superposition is we would take the actual structure, and when we say structure, we just mean the physical structure, and we're going to break those 2 loads up into 2 separate loadings. So we've got a structure 1 that has only the 200 kip load at the end. Structure 2 would have the 400 kip load at 10 feet. And so the solution of structure 1 and structure 2 may be simpler, maybe quicker. You can imagine if we were trying to find the deflection out there at the end, we could do that more quickly than we could up here. And any quantity, this is true for any quantity to solve for. Internal forces, displacements, stresses, strains. The problem has to be linear, and any quantity in the actual structure could be solved for by the summation of these structures 1 and 2, and there could be more structures depending on the loading or depending on the structure itself. All right, this is true at any location. So let's take a look at another application here with a beam in the transverse direction, which is what we've been studying lately. So the actual structure is a simple cantilever. That cantilever has 3 different loads on it. A distributed load. So these 3 loads are going to be broken up, and we're going to then compose the actual structure as a summation of 3 structures. One's going to have the point load at the end. There's the 10 kip point load. One's going to have a distributed load that only goes over 10 feet. And the other one would have the applied moment, and it is located at 15 feet along the beam. So we could go ahead and solve structure 1, 2, and 3 using statics. We can find internal forces, but let's focus in on the deflection here for just a moment. And as we look at what these loads do to this structure, I end up with a beam that bends down, right, due to the point load. I end up with a beam that also bends down, and then something interesting happens. Right? The last 10 feet of the beam has 0 internal moment, so that part of the beam is then going to be straight lined. So it'll have no curvature because there's no moment in it. So we're going to have a solution scheme, a superposition scheme, to help us solve for the deflection all the way out at the end of the beam. And same thing happens with an applied moment. If we draw the deflected shape, we get curvature or displacement up from positive curvature, and then we end up with a segment of the beam that has a straight line. And over those last 5 feet, if we cut that beam open, we find that it has 0 moment inside of it. So to calculate the deflection at the end of the beam, and technically it would also occur, we would have this need anywhere past 10 feet on the beam, which is where the distributed load stops being applied. We're going to have this same issue that occurs. So let's take a look a little bit closer here at the distributed load beam. So if we were going to use the beam equation, we would have 2 pieces that we'd have to deal with. We have a function m of x, and there's our x coordinate. So we would have 2 different cuts that we'd have to take. Down here we'd have a cut for x from 0 to 10 feet, right? It's applicable only from 0 to 10 feet right there. We would have to take a separate cut from 10 to 20 feet. And there's where we see that m of x would equal 0. Down here, m of x would not equal 0. So the way we would deal with this in the beam equation would be to solve those two pieces. Right? We would start with the left-hand side from 0 to 10, because over at the wall we have two existing boundary conditions. And as we go work our way back to the picture, so there's our two boundary conditions that we would know. So we'd be able to solve this all the way up to 10 feet. Now beyond 10 feet, right, we know the internal moment, but we actually don't know any boundary conditions just by looking at the picture. But we actually do know them once we've solved for the beam equation over the first 10 feet. We know that the deflection at 10 feet on the left would have to be the same as on the right. And it would also have to be true for the slope. And those are called continuity conditions. So at 10 feet, the deflections in the beam would have to be the same. Our beam has to be in the same location, and the beam would have to have the same slope. And so those would become the boundary conditions. Right? For segment 2, the answer for segment 1 would become those boundary conditions. And now how do we end up taking advantage of the fact that we have a segment on our beam that actually has 0 moment without doing the beam equation? How can we use superposition? And so there's our curved section. We've got a straight line section, and we are going to attack this by geometry. Now this deflection is drawn big, but it's extremely small. We only draw it big so that we can see it. So the approximation that distance is equal to the slope times the distance is valid, and that gets down to using tangent theta is approximately equal to theta for very small angles. So we end up using a small angle approximation, which is extremely valid. So the way that we get out to 20 feet is we take the deflection at 10 feet and we multiply, which is sitting here. And we're going to add to it the slope at 10 feet multiplied by the distance. And in this case, it happens to be 10 feet. So we multiply slope times distance, and that would get us then all the way out to the end of the beam. So there's our slope times 10. If we wanted to find the deflection at 17 feet, we would use the answer for deflection at 10, the slope at 10, and we would then multiply by a distance of 7 feet. So the last thing to hit on our discussion, we will do this in class quite a bit, but dealing with overhangs. And so we have a simply supported beam that has an overhang here. And what you're asked to do is find the deflection in this beam all the way out here at the free end of the beam. So if we circle back to the way that we would do this until now, we would need to go and do the beam equation. And we would have an expression for m of x here. We would have a different m of x here. We would call that segment 2. This would be segment 1. The thing that changes the moment diagram are two things. One is the force that's applied through the external restraint, and also the distributed load stops. So we have a change in loading. So we're going to have a change in the internal moment in our beam. So we'd have to do two different beam equations, and we would work our way through continuity across the roller to eventually find our solution out at the end. So we go ahead and cut. We'd have M1, we'd have M2. They would not be the same. We'd start over in segment 1. We would apply boundary conditions that we know in segment 1. We know the pin and the roller exist in segment 1. So there's the two boundary conditions that we would need. We would then use continuity to get out to segment 2. The fact that the answer in segment 1 would have to equal the displacement in segment 2. We happen to know it's 0 because that's at the roller. We don't know the slope in segment 2 at 10 feet, but we can calculate it by using the answer for segment 1 at 10 feet. So there would be our continuity, and we would just have to perform 2 beam equation calculations. So how are we going to do this? By superposition. Again, we will do this in class a few times as well. So let's approach this as we would any superposition problem. This is our actual beam. And this is a determinate beam. I've got 2 external supports. I've got 1 there. So this is determinate. So what I'm going to do is take the exact same beam and I'm going to break up the loading. So here in structure 1, we have a beam that has only the distributed load between 0 and 10. Right? The point load is gone. The point load is sitting down here in structure 2. So if I could find the deflection at the free end in structure 1 and structure 2, I can add the answer up and I would get the deflection in the actual structure. So the deflection at the free end out here, let's go ahead and draw a deformed shape. And now in structure 1, we have a segment where we have 0 moment. So we've got straight lines. So we're going to use geometry to get ourselves out there. That's going to be theta at the roller times 5 feet. And so the question now is, well, how do we find the slope right there? And we're going to have some tools. We're going to have a deflection table that's going to help us. Now, the one that's a little tougher to apply is the cantilever, the cantilevered overhang with the point load out here at the end. And so the thing to think about is that although we have no loads here between the pin and the roller, we definitely have moment in there. We'll explore that a little bit more in class, but there is moment sitting in there. The moment is going to change on the other side of the roller because that roller applies a load to the structure. So the moment is going to change. And so we're going to add 2 pieces together to get ourselves all the way out to the end of the member here. I'm going to take theta at the roller times 5 feet plus the flexure that occurs in the 5 feet going from the roller to the free end of the beam. So I'm going, dang it. So we can start to make even more sense of this by drawing a deflected shape for our beam. And that's what the deflection is going to look like from this cantilever with a point load at the end. So the way that we're going to break this thing up is we're going to use the slope right there. And if we extend it out, we get a value right there, theta at the roller times 5 feet plus flexure. And so this is how we use superposition to help us with this structure. So this is how we analyze it, and we'll end up using our deflection tables to do it. We're going to create a statically equivalent point load. So that 10 kip load that was sitting out at the end, we're going to make a statically equivalent force couple system back at the roller. That gives us something that is now in the deflection table. We've got it simply supported with an applied moment at the end. And so we can use the table to help us find theta at the roller. That theta at the roller is going to be multiplied by the 5 feet to get us out to the end of the beam. And then we have to add in flexure, which we isolate by analyzing the last 5 feet as if it were fixed. It's not exactly fixed, but we can capture just the flexure. So that's what the benefit of doing it this way is. We can use the deflection tables.